A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be having a lecture on the topic of material and spatial coordinates. So let us get started. The topics for today's discussion will start with material coordinates, also known as reference coordinates, and then we'll move on to the other type of coordinates that we use to express configurations, and that is called spatial coordinates. We'll talk about expressing configurations, motion, and particularly deformation in the spatial coordinates. Towards the end, we'll talk about finding the trajectories, velocity fields, and acceleration fields for motion expressed in these coordinate systems. So let us start with material coordinates. So in the last lecture, we talked about the idea of a reference configuration. So a reference configuration is a configuration that the body assumes at some time, or it can be a hypothetical configuration of the body, and we expressed this configuration as a function where we said that we can find the position coordinate of a given point using its ID like this. So this is the particle ID, and this is the coordinates of the particle in our chosen coordinate system, that is O, x1, x2, x3. So we have a point P here whose ID can be called just as a label P. So if I pass the ID of P to this mapping or the function phi, that will give us the position coordinate of the particle P. I can write this vector capital X as its components x1 I1 hat plus x2 I2 hat plus x3 I3 hat, where these capital I1, I2 and I3 are basically unit vectors in the three coordinate directions. So this is I1 hat, this is I2 hat, and this is I3 hat. Now you may be wondering, why is it that we are not calling these E1 hat, E2 hat and E3 hat? This is just our choice because we have chosen a certain coordinate system, and for this chosen coordinate system we are calling the unit vectors as I1 hat, I2 hat and I3 hat. And this is a particular choice because this is chosen to express the reference configuration of the body. So using our summation convention, we can write this as x a I a hat. So in the reference coordinate system that we have chosen, let's write it down. So here O, x1, x2, x3 is called our reference coordinate system. And when we express a vector capital X using its components in the reference coordinate system, these components are called reference coordinates or material coordinates of the particle with an ID x. Well, in this case, it's xp because I've expressed the position of point P. But in general, for a general point in the body, we will not have a superscript. We'll simply say that capital X, which is a position vector of some point in the body, in the reference configuration is written as capital XA times IA hat. Now please note that it is our choice that we have chosen OX1, X2, X3 as the coordinate system to express the capital X vector. The capital X vector is dependent on the reference configuration. If I had chosen a different coordinate system, that is different origin and different unit vector directions, I would have expressed capital X vector in a different component form. But the vector physically does not depend on our choice of coordinate system. It depends on our choice of the reference configuration. And I must make a note here that capital letters, as you can see here, we are using capital letter A, are used for indices when vectors or tensors are expressed in the reference coordinate system. So in this reference configuration, which is expressed using the reference or the material coordinate system, an ID for a particle P corresponds uniquely to a position in the reference coordinate system. Remember, we talked about a one-to-one correspondence. So for this point P, which has this ID, it is this position which is expressed in this OX1, X2, X3 coordinate system. There is a unique mapping between these two. So instead of writing XP, I can also write the vector capital X to identify the particle. And this is possible because the reference configuration is unique. It's a very important point because till now I was referring to the particle P using its ID. Now I can also refer to the particle P using a position vector, which is this capital XP. Because the reference configuration is unique and my choice of the reference of the material coordinate system is also decided, so I can express these coordinates x1, x2 and x3 for the point P, and once I have chosen these coordinates, I uniquely locate a point in space, which is this point here, and that will correspond to the particle P because this is our chosen reference configuration. So in mechanics, while referring to particles or points or material points, it is more convenient to refer to them using their material coordinates. So we use capital XP to identify the point P. So if I give you capital X vector, which corresponds to some point in space, it will be only one point that was there at that point in space in the reference configuration. So this uniquely corresponds to some point, some material point. Of course, you have to specify your choice of reference configuration. Had you chosen a different reference configuration, a different point would have been sitting in this spatial location, so it would have referred to a different point. So this is uniquely specified for a chosen reference configuration. So in a way, I can say that XP is a label for the material point P. So instead of using IDs now, I'll be labeling points using their material coordinates. And this is the reason the word material coordinates is called material coordinates, because these coordinates refer to material points in the body. I'll give you an analogy which will make it easier to remember. Say that you are teaching a class and this is your first lecture, and you see the class, you can see people, students in the class, and instead of remembering the name of a student, you remember that this is the student who was sitting in the front row in the center seat, because you visually remember that. So this is called material coordinates. Instead of remembering the ID or the name of the person, you remember the person's location in space, that is the front center seat, on a particular reference day, that is the first lecture of the course. And this is something we do all the time. We choose to give IDs to objects or people based on their location in space on a certain day, or in the language of continuum mechanics, in a certain configuration, which we call the reference configuration. Now, since there's a one-to-one correspondence between the particle's ID and particle's location in the reference coordinate system for the chosen reference configuration, we can define an inverse mapping as well. So in this inverse mapping, if we specify the position of the particle in the reference configuration, it will give us back the ID of the particle. Right, so now we are ready to define motion, that is configurations evolving with time, or a sequence of configurations as we called. So earlier we had written that as the body deforms or moves, we define a function kappa, which is a function of the particle's ID and time. So as the body goes from one configuration to the other, the point P will move from P to P prime to P double prime and so on. So if I specify the ID of the particle and the time, so this is T0, T1, T2 and so on. So if I specify the ID of the particle and the time t, it will give me the spatial location of the particle at that time. Now, since we are interested to specify the labels for the particles using the material coordinates, we can substitute the inverse mapping in this kappa function. So this gives us the spatial position of a particle P, let's call it for a particle P, is kappa, and we replace phi inverse of x vector, capital X vector, comma t. So this gives us a function chi, which is a function of capital X and t. And again, this is right now being specified for a particle P. So I've put a superscript P with all position vectors. But this is true for any particle in the body. So I don't need to specify P here on superscripts. I can remove that, and that very well works. So capital X is the position vector for some particle in its reference configuration, that is its material coordinates. And when you specify a particle which uniquely is specified by capital X and the corresponding time, what you will get from this mapping kappa or the function kappa is the spatial location of that particle at the time specified. So the function chi describes the motion of particles in space as a function of the position of particle in its reference configuration. And remember, the reference configuration or the material coordinates simply are labels or identification for some point. Again, with the same analogy as we just discussed earlier, if I say that find the current seat number of the student who was sitting on seat 1C on day 1. So what that means is the current seat number corresponds to the spatial coordinates right now, that is at t equal to now, and I'm referring to that student as the student who was sitting on a specified seat, that is seat 1C on day 1. So seat 1C on day 1 basically is a given point in the reference configuration, that is day 1. As the day changes, the student may be sitting at different locations in the class, and these locations will be the position in the space at later times. And just the way we had chosen a coordinate system to express our reference configuration points, we choose a coordinate system to specify points in the spatial configuration. So let us say this is our material coordinate system OX1, X2, X3 with capital X's, and I choose a different origin. I'll call it O prime with a different orientation for the axes. We'll call it small x1, small x2 and small x3. So here O capital X1, capital X2, capital X3 is the material coordinate system, and O prime small x1, small x2, small x3 is our spatial coordinate system. So these are chosen by us for expressing points or position vectors. And as we see here that they are completely different. In fact, these coordinate systems can also rotate with time. That is also allowed. So depending on our convenience, we will choose these coordinate systems to express points in the reference configuration and points in later configurations. So as we said that this small x vector will be used to express points that the body takes in configurations at later times. So these xi's are called spatial coordinates, and these ei's are unit vectors in our spatial coordinate system, that is O prime x1, x2, x3 with the small x's. So I'll highlight the unit vectors as well in the green coordinate system. So as we said that it is our choice to decide on the origin and the directions of the unit vectors in the material coordinate system as well as the spatial coordinate system. So nothing is stopping us to choose the same coordinate system for both. And that is what we typically do unless the problem demands a different choice of the coordinate system. But whatever derivations or definitions we'll have for quantities in expressing kinematics will be independent of the choice of material and spatial coordinate systems. So for convenience, we take the same coordinate system, as you can see, to express material points, that is points in the reference configuration, and spatial points, that is points in all later configurations. So going back to the chi function, which helps us find out the spatial coordinates, that is small x, given the material coordinates, that is capital X, which is basically a label for the points in the body and at a given time. So this chi is a vector function because it returns a vector. In fact, just the way we write sometimes y, which is a function of x, as y is just y as a function of x. So instead of using f, we use the same variable y to express the function as well as to express the output value. We do that here as well. So we write the position or the spatial coordinates is the function small x vector of capital X comma t. So note that this is a vector and this is a function, but the output of the function is the vector, that is the spatial coordinates. So this function chi or the function small x vector is one of the most important functions that we are interested in to quantify motion in continuum mechanics. Now let's see what happens if you try to find the function chi at time t equal to 0. So this basically gives us the position of all the points at t equal to 0, and that is exactly what we call the initial configuration. And in case our choice of reference configuration, which is denoted by this capital X, is the same as the initial configuration, because we said that the most intuitive choice for reference configuration is the configuration of the body at t equal to 0. So if the initial configuration is taken as the reference configuration, we get the function chi for capital X comma 0 as capital X. So this is a good check. If you have the function chi given to you, which basically tells us the configuration that the body takes at all times t, we can put t equal to 0, and if we get the same vector x, capital X, then that means that we had chosen the initial configuration as the reference configuration. This will become more clear when we solve problems later in this week. Now with this, we have defined motion. Because what is motion? Motion is the body going from one configuration to the other. In fact, it is the body taking a sequence of configurations from the beginning to the end. So the beginning is the initial configuration and all later configurations are deformed configurations. So in this case, the function chi specifies all that information. So with that knowledge, we will sometimes want to find trajectories of certain points in the body. So for example, if one is trying to map the facial features with the movement of lips or eyes, for example, they'll want to have the initial configuration as the configuration of the facial points at some initial time, and then as the face deforms, that is, the eyes or the skin points move, they'll want to see the later configuration. So they'll want to see how a point on the face moves from the initial configuration to the later configuration. And if I want to map the complete path of a given material point, that is a point on the face as a function of time, I'll see a movement of that point. If I had a fluorescent dye and some specialized lighting and camera, I could see that the point moves from start, that is the initial position, to some end. So I can find the trajectory of some point P using the chi function, where we pass in the initial material coordinate of the point P and the time. Of course, trajectory requires us to get rid of the time variable because we're interested in the path that the point P takes in the spatial coordinate system. And again, this will get clear when we solve problems. Next is we are interested in velocity of points. Since we have trajectory, which is the position of the point at different times, we can differentiate that to get the velocity. So the velocity of a point P is d by dt of the position vector of the point P, which is basically d by dt of whatever is returned by the chi function, and this sometimes is written as chi dot because time derivatives are written with a dot on the top typically, and we put a p on the top of chi because we're talking about the point P that is denoted with its material coordinates capital XP. And of course, this is at a certain time that we are interested in. But if we want to get the general expression of the velocity of the point P, we'll keep it general in the variable time. Now, chi typically will be a function of x1, x2, and x3. That is the meaning of the position vector capital X and time, of course. So if I differentiate this with respect to time, so this will be expressed using the chain rule as del chi by del x1 times dx1 by dt plus del chi by del x2 times dx2 by dt and so on. Now what about these terms? I want you to pause and think about it. What exactly are these terms? And I'm sure you've figured it out now that these are zeros. And the reason for that is because capital X vector is the reference configuration. It is the configuration of body at a given time, typically t equals 0. So if this capital X is a position that is defined at t equal to 0, that means it does not depend on time. So the components capital X1, capital X2 and capital X3 are independent of time. So these terms are 0. So what we are left with is simply del chi by del t. So I can write here that this is del by del t of chi for the point P. Again, these ideas get better when you solve problems. So I'll just write here that del capital X by del t is 0 from definition of material coordinates. Now we define the velocity of a point P, but typically we'll talk in terms of a velocity field, that is velocity of any given point. So that velocity field will be expressed as a dot of the position field, that is small x vector, which basically means it's del by del t of small x, which is a function of capital X and t. Again, I am using small x as a vector for the position as well as for the function in replacement to the chi function. And the acceleration field A is written as v dot or small x with a double dot. So this brings us to the end of this lecture. In today's lecture, we talked about two very important ideas, that are the ideas of material coordinates and spatial coordinates. Material coordinates are an important idea and quite confusing sometimes as well, because they are used to specify the labels for points in the body. They're not just coordinates of points, they're basically proxies for labels to different points in the body, which of course corresponds to the reference configuration. And spatial coordinates are more intuitive in nature because they simply denote the position of different points in space at different times. The understanding of these coordinate systems is essential to be able to understand the quantities we'll be defining later this week and in the next 2 weeks. Most of the confusion arises typically in kinematics, in continuum mechanics, is because of a lack of clear understanding of the definition of different coordinate systems. In the lecture to come, we will talk about two related ideas, that is, expressing physical and other geometrical quantities in these material and spatial coordinates. And this will give rise to the Lagrangian and Eulerian description of quantities in continuum mechanics. So thank you very much, and I will see you in the next lecture.